remember the word for my merit. Slowly.
How about the exam
That's
for the mathematics physics?
They were pretty good.
That's good.
Is it good?
Yeah.
Good.
Studying to exhaustion paid off.
So what kind of level, we already discussed a special differential equation?
Yes, we
Like
covered
what kind?
hypergeometric
Hypergeometry,
differential
already,
equations,
okay,
series,
so Bessel or,
Green's
okay.
functions, eigenfunction.
Good, so next spring
Good
we
ones.
want to go discuss quantum.
Yeah.
Yeah, good.
Yeah.
So
Good.
So then orthogonality of Laguerre polynomial. But the exam,
on the test,
yeah, on the test we asked
just to find the decimal.
Bessel.
Yeah,
Yeah, I forgot it too.
I just tried, I don't really follow.
Oh, did you write the Legendre?
Just tried.
But the question is.
I mean, I can reason out what it is. It's equal to 0. It's like, what is the form now?
But the question is about write the relation without deriving from the
Yes.
relation
Just-
Yeah, so
generating.
Just try to relation.
Yeah, I think so.
should have gone over that. I knew we were forgetting something.
I said that restart.
Well, studying really helped. Well, yeah, helps. Now we can do that every week.
What they say, Fatima left earlier
Yeah, I'm not
in
sure.
test 2. She told me that she need to focus, she want to read alone, she want to study alone because she want to focus.
How about doing a test?
Yeah, but I think she left early.
Yeah, studying alone does that to you. You're more prone to distractions and
But I prefer to study in a group.
you do?
Yeah.
Me too. Because we actually are productive. Because if I get stuck on a problem,
Have
then,
you watched
you guys know it. Have you guys get stuck?
Have you watched the video?
Is she already posted?
Qualified. He's asking.
Oh. You guys are pretty funny these days. You guys are teaching me your language and making jokes. That's it.
You need to keep it. You need to keep it secret.
All right. Thank you. Let's start it. Just remind you with we start from chapter 8 and the goal of chapter 8 at the beginning is try to transfer from the Lagrangian formulation mechanism to the Hamiltonian formulation mechanism. The goal is, as I mentioned, that the equation of motion in Lagrange, a Lagrangian formulation mechanism is a second-order partial differential equation, and in most cases difficult. And our goal is try to reduce the second order to the first order partial differential equation, right? So how to do that? We use this Legendre transformation technique, right? Try to transform Lagrangian to the Hamiltonian by this way, and how to define this way we discussed. So the difference is here. In Lagrangian formulation mechanism, we just define the variable, which is n independent general coordinates in the convolution space. So this n dimension. But in this Hamiltonian formulation mechanism, we introduce Qj and Pj both as the individual or independent variables, and build up two n-dimension phase space, right? So that space is A. And then under this one, so that function of Hamiltonians be function of Qj, Pj, and time. So we apply the Legendre transformation, we can define this Hamiltonian. Then what we found by, because here's L, right? By introduce this, find this total differential of dl dh substitute to here, so we can find finally this dh is this first term is qj dot dpj minus summation of pj dot dqj and minus partial L times t. But function, since h is a function of qj, pj, t, so that's also equal to this term. Then by comparing both be equal, so we found this, this we call the canonical. Equations of Hamilton. So you can see here the qj dot is simply the partial h with respect to the conjugate momentum, and the pj dot is negative partial h with partial qj, and the time partial, the partial derivative of time of h with t, that is just negative of partial L with t. So it's here really reduced to the first order partial differential equation, and make this show this equation become easier. But as I said, if you go to the details, it's not very straightforward. We still have some of equations, they are has a cross term, so they are not independent of each other. Then we solve it, we still need a technique. But this technique, it is still can extend into detail general, which we are going to discuss in chapter 9 and chapter 10. But chapter 8 first gave the idea. Then now we are going to discuss or compare results between the what we familiar with Lagrangian and now introduced Hamiltonian. Some of these terms are similar as and we can just take some discussion from for the Lagrangian formulation mechanism and transfer to this Hamiltonian formulation mechanism. First, okay. First one is I think maybe I use this. Remember, we have introduced the energy function in this one, right? If you remember, so now let's see the energy function. H. But H is a function of Qj dot T. So that means this quantity we defined in this convolution space. So if you remember, we defined this one is nothing but this summation Qj, and which is Pj Qj dot minus L. Same formula like this. But this is a function of Qj dot. Since Pj here, that is conjugate momentum, define this. Now, okay, that is in the convolution space. Now the Hamiltonian we have here, I already write down here, so I just rewrite again. But here you see the formula same, but this is a function in this phase space. We are going to transform these variables from this convolution space to the phase space. So with this, then if you remember this class, we discussed this is energy function in general is not equal to energy, right? System. It depends on some condition. Here, the Hamiltonian have same thing. So if just discuss, let's say, because remember we read L is in terms of L naught plus L1 plus L2, right? That is in terms of the QJ dot. In terms of QJ dot. Zeroth order, first order, second order. This is zeroth order, right? First order, second order, or conjecture. If you remember this, then let's see. Okay. So now it's what we are going to discuss is this one, but they are similar. So if the partial R partial t equal to 0. Remember this? So if this case, then this L naught is equal to minus V naught, and L1 is equal to minus V1. V1 is if we have the potential also function of a general velocity, so that is include L1. But then the L2 is only T2, which is T. Then further, that is a first condition. Second condition, if this false, it also can be written as a gradient of any scale potential, negative potential Vi. Then we have L1 equal to 0. That means no V1. That means potential only function of general coordinates, not general velocity. Then here, we have L1 equals 0, so then finally, you can see here, Hamiltonian. Okay, use this. So now Hamiltonian is equal to summation Pj Qj dot, and then the minus T, right? Okay, the T2 is equal to T, and plus V naught. And then, okay, now we need another. So for this term, we use, if you remember Euler, we use this, Euler's theorem. That summation for J, Pj Qj dot is equal to summation J, that is partial L. Pj is partial L, partial Qj dot, right? Qj dot. So that is leg x and partial f, partial x. In this case, that's be equal to the order is first, n is, okay, let's see. All right. Now here, since L, in this case, if these two conditions satisfied, L naught is constant, so that is not function of Qj dot. L1 is also 0. So when we partial L, it's partial L2, partial Qj dot. Qj dot. L2 is second order, right? So that is 2 of this L2, right? Second order of the function, second order of Qj dot. This, remember this theorem is, let me, xj partial f partial xj equal to nf. That is Euler theorem, remember? So now this xj in this case is Qj dot. Then the Pj is partial L, partial Qj dot. Partial L, since L naught and L1 is 0, L naught is the 0th order of this. So the partial L, partial Qj dot is nothing but the projector. And the projector is nothing but the term is T, right? So that is 2T. And we use this, now we are going to substitute Hamiltonian is 2t minus t plus V naught, which is t plus V naught, which is energy. Just remind, when we discuss the energy function in chapter 2, we do the same analysis. That case, in the configuration space, the energy function is equal to energy when these two conditions satisfied. Now in the Hamiltonian, similarly, if we find that the R does not depend on time explicitly, and also the potential is a function of, negative gradient of this scalar field, then we can immediately get this Hamiltonian is not equal to energy. And that is the most case satisfied, right? So just keep in mind, this is also why we are interested in the Hamiltonian, that in most cases, this is nothing but this energy. Okay. So with this discussion, now we are going to more practical, right? So now, okay, from the Lagrange transformation, we can transform the Lagrangian to the Hamiltonian. Now we are going to do the practical how to transform. This gives a theory. Now for giving a system, we how to write this Hamiltonian, right? So now we are going to see, we give this procedure. To construct, or transform, to construct Hamiltonian. Okay, I just say H from L, right? So I just to save this bit from Lagrange. So we just, in general, we have several steps. Step one. Step one, just construct, first we construct L, right? And L is simple. L is equal to T minus V. So you need to find T and V, right? But given different system, we have a T and V. So that is function of general coordinates, general velocity and time in general. And of course, this one we already familiar. Chapter 1, chapter 2, we did a lot. How to do that? How to find the kinetic energy, how to find the potential energy. First, you need to select these general coordinates, right? Once we have a general coordinate, we can write the kinetic energy and potential energy, then we got the Lagrangian. So that's step one. Then go to next one, step 2. Calculate the conjugate momentum, Pj. Once we have a L, the Lagrangian, so we can calculate this, right? G from 1 to n. How many we have? Depend on how many general coordinates. Okay, once we have this, now we can write the Hamiltonian. So Hamiltonian, construct Hamiltonian. Okay. All right. Okay, H by definition is summation for P, the product Pj Qj dot minus L. So we have L, we have Pj here. You just use this because this is variable. So here you just write Pj dot. You don't need substitute this formula here. We are going to use this formula to replace this Qj dot, right? So okay, here and you will see this is a case of a mixture of Qj dot, and Pj and time. So this case you have mix of these two. Then the next step, we are going to get rid of Qj dot, right? Since Hamiltonian, we want to find the Hamiltonian is in the phase space, right? So that's be Qj, Pj, T. But here we have a Qj dot. So that is convert Qj dot to Pj and Qj, maybe also. So that is negative. How to do that? From Pj is partial L partial Qj dot, which is a function of Qj dot, and T, right? And from here you're going to find Qj dot is function of Qj, Pj, and time. Then the last step, step 5. Okay, once we have the QG dot, so then they substitute all the QG dot into Hamiltonian. Then finally your Hamiltonian is a function of all the function of QG and TG. Okay, so that is the step by step how to convert or construct Hamiltonian. Now let's do some examples and see how it works. Here.
Thank
Yes.
you. What do you mean by mix?
Mixture of PG and QG dot here. Because there's a QG dot. Since here there's a QG dot,
Oh,
right?
yeah.
Here we also have QG dot.
Okay.
So the next job is try to replace QG dot in terms of QG and PG.
Okay, thank you.
Okay, so now let's do some examples. Example 1. Let's consider this is we also did before, chapter 1, chapter 2. We have a loop. Rolling down without slipping on this decline, right? So here is this center. Suppose the loop you have a radius r, and at any case, this project. This is angle, theta, center of mass here. So now, if we suppose if this length of this one is L, then the distance of the center mass from the top to any position, I'm going to use x. Right, the perpendicular to, so at this position that is x, and the total length is L, and the angle of this decline is phi. Okay, now we are going to construct Hamiltonian for this system. So now let's do that first. Step 1, right? Step 1 here, this one, I just, there are some details, right? So first, that Q, which, in this case, which general coordinate we are going to select? Since here, this is rotation, right? And then this rotation is the center mass move, include the rotation. So how many general coordinates we are going to need? We need 2. Which one? X and theta, right? So only these 2 we are going to select, and they are independent. Yes. Okay. So with these 2, I select as a general coordinate. Then we can select write down kinetic energy. Kinetic energy, as I said, you can write in terms of sum over all the particles in the system, or in terms of the center of mass kinetic energy and the relative kinetic energy, right? In this case, it is easier to use this, right? And center mass is just do this linear motion, so that is a half of total mass x dot, right? That is only depend on x. And the relative potential, the kinetic energy is all the mass on the loop, right? Rotate about the center of mass, so we know this formula. Oh yes. We know this formula is m. This is m r squared, which is moment inertia, right? And theta plus 1. So that is first step. If you write down this correctly, then the following is just step by step. So here, this is always at the beginning. You think about which general coordinate you will select. Then kinetic energy. Now potential energy. Here, potential energy depend on, this is only the rotational potential energy, right? So in this case, since there's a center mass, we just consider this is a mass move down. depending on where you're going to select this zero potential, let me write down and then I'm going to this. So that is mg. And this the head, right? The head is L minus x sine phi. Here, I select, I think, if this loop go to the horizontal plane, that is here, right? So this is center mass here. I'm going to select this one as v equal to 0. So then, do you understand what I mean? So because I just looked the center mass position, though the center mass when the horizontal at this position I select. So this is a h naught as the 0 reference. Then each one is the height, right? This h, right? And this h is this length because the angle is the same, right? So this length is L minus x and multiply sine. So that is this one. Okay. So the potential I write down then very easily. I think I can use this here. L P minus V, so that is half of minus m x dot squared plus half of m r squared theta dot squared minus m g L minus x sine. This angle is constant, right? So this one is constant. Okay, so now you will see here the L is function of x, theta, x dot, theta dot, right? No time, so that's not depend on time explicitly. So that is the first step. We write down this in terms of the general coordinates, general velocity. Then we go to the step 2. We are going to find the conjugate momentum. Step 2. So P, we have how many? We have 2, right? Px we partial L, partial x dot. And here that is mx dot, right? And P theta partial L, partial theta dot, which is here. This one is mr squared theta dot. Because we are going to use this in step 4 to convert qj dot to pj, right? So let's first calculate this. Then we go to step 3. We are going to construct Hamiltonian. Hamiltonian, by definition, that is P, first one, Px x dot plus P theta theta dot, right? Minus L. Now L is here, so now let's just substitute. So here Px P theta is by definition. Here, by this definition, so we already have to. Then you can see, let me just write down here. Px x dot plus P theta theta dot minus L. L is half of mx dot squared minus half of m r squared theta dot squared and plus mg L minus x sine phi. Then you can see here, in this case, we have a pj, we have j dot, qj dot, right? That is a mixture of this pg and qj dot. So in step 4, it is not final formula of this Hamiltonian since we get rid of this qj dot. So that is step 4 we are going to do. Step 3, we write down the Hamiltonian now. Step 4, we are going to find the function of the qj dot as function of pj and qj. So now, let's look first this one, right? From px, that's equal to x, so that very easily from, okay. From px, we're going to get x dot. So x dot is px over n, right? You have question? Okay, from here. Then now, similarly, from p theta, we're going to get theta dot is from this formula. So theta dot is p theta over m r squared. This case is simple since this formula is very short and very clear. Just x dot with px dot. There's no any other term, right? So that case, this is an easy case, but we just do from easy and go to the complicated. So now we go to step 5. Okay, so finally we are going to substitute x dot qj dot theta dot to the x Hamiltonian. So now let's first px and x dot is px over m. Then p theta dot is p theta over m r squared. Then minus half of m x dot squared. So that is px over m squared. And minus half of m r squared theta dot squared. That is p theta over m r squared squared. And plus mt mu minus x sin phi. So now you see we have no any qj dot, right? All pj over qj, right? So now we are going to combine some terms together. So here is px squared over m. We have a half of pm squared because m squared, mm became a denominator, right? So this one becomes half of px squared over m. This term combined together. And this term, they are also same, right? So you see here, this m r squared and divided by this one, so we have another term. So plus half of p theta squared over m r squared. Then plus the potential. Okay, that is finally we construct Hamiltonian from the Lagrangian to the Hamiltonian. And this one is very easily, you know that is this one, right? So that is energy. But you can also check, because here partial R, partial T is 0, since we have this, whatever x, this position, right, vector is 0, and also the potential here is negative of this gravitational potential. So immediately we know that it's equal to this. And yes, we found out the case. Okay, so that is the first example. Second example, I'm going to take your qualified exam. Use that problem to construct Hamiltonian. I think now you know that problem you can do because this is a central force problem, right? Yes. So in that time I have not discussed chapter 3, so that maybe I'm familiar with this. Now example 2. Okay. The force, just follow that. The force given us is negative. It's a central force. But to this RQ, right? So R unit vector. This unit vector, R hat is unit vector. That is the only information they gave us and ask us to find. Let's just, if we have the central force problem like this, how to construct Hamiltonian. Okay. Now, first, step 1, we are going to select the general coordinates. How to select general coordinates? We need to know what's the motion of this particle, central force particle, right? So because here we need first, let me get. Step 1, try to find this, right? To answer this question, let's look. Because the force is parallel to the R, right? Okay, just R hat is R. So this the torque is R cross F, right? This is almost the same analysis when we analyzed the central force at the beginning of chapter 3. Therefore, we know the torque is dynamics of the angular momentum. This L, I use vector, so this is not Lagrangian, right? This is angular momentum. So that equal to 0 means it's conserved, right? angular momentum is conserved. So vertical motion, the particle it move around the angular momentum, so that means this it is okay. The motion is perpendicular to angular momentum, right? Since angular momentum is constant, so all the motions be always perpendicular to this one. So here we can select like this, right? If this angular momentum, if it's a closed or bounded states, right? Something like this. So that means it is confined. This is the first question I think asked, right? Confined in 2D, right? Not 3D. In 2D, and this 2D, which is a perpendicular 2D plane, which is perpendicular to L, right? That is C first. And then you can select general coordinates. So we can select the polar, because polar is better to describe this central force from polar coordinates. So here, x, y, and then select z. If we select particle, the L is just parallel to z, so we have this any position, this is r, and that gives us r and theta. Any position here, right? So the q is r and theta. Okay, after here, so we found this. Then we can go to the next, write out the kinetic energy, potential energy, and Lagrange. So this step actually is need our knowledge, right? Okay, now let's write down this, so we can write down first. Actually, you know how to do directly, so, but I still follow what we learned in chapter 2. We need to write down the transformation equation that between the general coordinates and the real, right? The component x is r cosine theta, y is r sine theta. Then from here we can give it x dot, because kinetic energy is x and y, x dot, y dot, right? So that is r dot cosine theta minus r theta dot sine theta, right? Y dot is r dot sine theta plus r theta dot cosine theta. Then with this, so we have kinetic energy is half of m x dot squared plus y dot squared. But if you're familiar with polar coordinates, you just direct write down the final. Here I just, so when you substitute x dot y dot into here, and then finally you find out the r dot squared plus r squared theta dot squared, right? If you know this, immediately you just write down here. So kinetic energy we obtain. Now the potential energy. That is also one of question. I mean, include that the question, but you need this potential, right? So how to find potential? I found some of you use integral. Yes, that is fine. But very easily, because the force is gradient of potential, right? So that is minus k. So you immediately know this potential. I just write down. Okay, thank you. So potential, you just do the gradient. That's be negative k over 2r squared, right? Let's do that. If you do the gradient, 2 cancel, and then you have a negative, but let me see. Yes, this is negative, so that one. Yeah. Then you have positive r cubed, right? K over r cubed, so that is this one. So you have this. Now we can write down the Lagrange, which is kinetic energy dot square r square theta dot square minus plus, right? So plus k over 2r. I think some mistake here I found. Some of mistake. I don't know who, but this is a this square, because the force is the cube, right? Not square. Okay, so now this is finished. This is step 1. Now we can go to the step 2. So we have r and q, right? Theta, right? So PR partial L partial r dot, and that is m r dot, right? Immediately. Then the p theta is partial L, partial theta dot. That is again m r squared theta dot. Then we go to step 3. For this, the qualifier exam, when you have this, you can apply the Lagrange equation, right? That's the details. I think up to here, the remaining part, you can do that. So, and also you see that theta is cyclic, right? So the L is constant, right? So that is, I will not discuss this. We just want to construct the Hamiltonian. So let's say Hamiltonian is PR R dot plus P theta dot minus L, right? By formula. And now let's substitute the L here. So we have PR R dot plus P theta dot minus half of M R dot squared plus R squared theta dot squared and minus K over R squared. So here, there's a mixture, right? So we need to find the R dot and theta dot and replace that or substitute that into the Hamiltonian. So finally we can get rid of this. So that we go to step 4. Okay, step 4 from PR. Let's say PR here, right? So we can immediately got the R dot is PR over M. Then from P theta, we're going to get the theta dot is P theta over M R squared. Then you can see here, not only P theta, but also the function R. In this case, right, to the P theta, the theta dot. Then we are going to go to the final step, substitute the R dot theta dot into the Hamiltonian. So Hamiltonian is PR, R dot is PR over M, then P theta dot is P theta, M over R squared, no squared, sorry. Then Hamiltonian, Lagrangian half of M R dot squared. R dot squared PR over M squared plus M R squared. Theta dot squared is P theta M R squared squared. And the potential, right? Potential is plus, minus, okay. Minus K over 2. Now this term, these two terms combined together, so we have a half of PR, I think, okay. PR squared over M, right? This term, and then this term, that term, plus P theta squared over M R squared. And minus K over 2R squared. And yes, that is nothing but energy. And again, you can check this condition definitely is also true. Potential force is the potential rate, right? So okay, that is the step which you can take. But there's another way we use the matrix representation to convert or construct Hamiltonian. So let's so easily, which one you prefer? I prefer use matrix, but you may prefer use it this way, right? So now alternately, we can use the matrix to construct Hamiltonian. how to do that, let's start from here. Remember the Lagrange, we can write the Lagrange in terms of zeroth order of the QJ dot. So this only function of QJ and time. Then the first order or linear term is L1, which is QJ dot and T, right? And plus the second order, which project term of the QJ dot T. Okay, so zeroth order, that means let's still keep here because it's a zeroth order. That is some values or numbers. Okay, this one, if it is QJ dot linear, right? So that's be something like a linear combination of coefficient A. A is be only function of QJ and time, and multiply QJ dot, right? That is L1 definition. Remember. And this L2 is this project term, which is to make the symmetric, so we use half of summation I and j, and we introduce the element, if you remember, Tij, which is only function of Qj, and T is not function of Qj dot. Then we have a Qj dot, Qi dot, Qj dot. The product of this one, Qi, Qj dot. Okay, so this is a Lagrangian we can write in terms of the generalized velocity. Then this way we can write further. This one's constant, so I still keep it. L naught is a sum of constant. I mean, sum of term only this or function of this QT and time. But this one, you see, this is a linear combination of these products. If in terms of this matrix representation, it's like this row and column, right? Like inner product. So I'm going to rewrite this way. Q dot, and let me give a name. First write down here, and then I will give explain. And here, okay, half of transfer T. Okay, here. Q. Okay, Q dot. Q dot is colon because it's there are QJ dot 1, Q dot 1, Q dot 2. So that is all this colon. So that is Q1 dot, Q2 dot. All right. So that is we can make this as a colon. Then the Q dot tutor, which is transport, which is row, right? Q1, Q2 dot. So then this product is like this row, which is QJ dot, multiply the colon A. So I give A, which is A1, another colon as a coefficient, which is a function of QJ and time. Then T. T here is this square matrix, which is T1, 1, and T1, 2, which is T1n, right? So that is n by n matrix. Okay. So then you can see the last term, this is a row multiply square matrix and the column. Then the final give us is again is like inner product, right? Like this one multiply the column here give a new column, and the row multiply column is inner product. So this is nothing but this is summation of this. Yes, if you're familiar with this one, is correspond to this. So now this is a matrix representation. So that is a matrix representation of Lagrange. With this representation, then we are going to write the Hamiltonian. Therefore, the Hamiltonian is by definition, right? Qj dot Pj minus L, right? So now I'm going to rewrite here. This one is also the inner product, right? So I'm going to write down as Q dot Qton, P, I'm going to P here, this product. And minus L, we have L naught, let's keep L L naught here, and L1 is this term, Q dot tutor is A, and minus half of Q dot tutor T Q dot. Then here, this one the same, right? So now I can take this outside, that is P minus A, and minus half, right? Move this term to the left end. Now, we're going to, because Hamiltonian, we need to get rid of this, right? This. So we're going to find how to find the relation. That is our step 4. Convert the from this PJ, convert and get this QJ dot in terms of PJ, right? So that one is this. Because we know the PJ is partial L, partial QJ dot, right? And L, we have L is 0th order, second order, first order, second order. So when we partial L partial QJ dot, this term here, right? So that is only partial L1 partial QJ dot plus partial L2 partial QJ dot, right? Partial L1 is AJ, right? Correspond to this. And then just use the matrix, because here was this is each term, so the P. So P as the matrix, column matrix, is this one, is this one gives us 8, right? Because here, when we partial QJ dot, is 8. And then that one is half of, since we first do this one, we have TQ dot and plus half of Q dot T, right? And again, we know this T has a symmetry. This one, we don't need proof. Later we do some examples, you will see this in all the case. This element is always symmetric. That means Ij equal to Ji. So here, this is Ij and this is Ji, right? This is I and Ij, this or Ji. So then they are the same. P we can rewrite is A plus T. Okay. So now the Q, then we can find Q dot. Move this to, so that is, move A first, and then you divide the T, so it's a T inverse, right? And the Q dot transport is P, yeah. Since here, you know the T transport because it's symmetric, right? Okay, then we can have, now we can have the final Hamiltonian is this one. So now I'm going to use the P tutor, A tutor, which is it's a complex conjugate, transport matrix, and T inverse, and then multiply P minus A. And then here, this term also, we have a half of, minus half of, again is P minus A, T inverse, and then T, and then here this one is T inverse, P minus A, and minus L naught, right? So you see these two terms just half, right? Here, this T minus 1, right? So this is T minus, this is T minus, this is the same. So finally, we have a half of P transport, that is rho of P, and P inverse P minus A times L naught. That is matrix representation for Hamiltonian. So in this way, what we need to do? Find this. Find A, then you find A. Find A. find L naught, and find this. So in this case, we are going to do several, but actually the details similar, but it also makes some of a step, maybe we can remove some steps. So here, in this case, if you use matrix representation, what you need to, you find A, find T, and L naught. From where? From here, Lagrange. So you need first to write down Lagrange in terms of matrix representation, or you just from the Lagrange matrix, you can find this. So now let's do some examples. See how we can let's do one example of this. To practice, so example 1, a particle move in a central force, right? So again, a kind of central force field. Okay. So in this case, we know the potential is only this. There's no velocity dependent, right? Because the central force, we know the force is function of, okay. The force, you just write down here. Central force, V, which is only function R, right? So that means the potential is only function R. That means V1 is 0. So what means V1 0? A, right? No first order or linear term of general velocity. So that is the first, okay. And then there's kinetic energy. Now we are going to, because we are going to find this. So the kinetic energy here, this was matrix. Now the kinetic energy is only the project term, no any other term, right? So that is here, half of m x dot square plus y dot square plus 3 dot square. In Cartesian, now we are going to, this ask use in the sphere, in spherical coordinates. That is question. So we're going to convert it into the spherical. How to do that? Something like we did before for the problem, right? So we just I think you know this. In the spherical, this term is r dot square, r square theta dot square and plus r square sine theta square and phi dot square. So first we need to write down the kinetic energy. And then you will see here, these are in terms of the dot, which is not any, all are projector, right? So that need your knowledge. Familiar with this, this is a linear product or the inner product actually. And how to write in terms of the matrix. Let me write down here. Matrix means, there it is, this term, right? Something like this. So that's if I want to write in terms of this product, and the result is only this r dot, theta dot, and phi dot. So that means the t is be diagonal term, right? So now let me write down. I hope you can understand. I know this is a little bit half of r dot, theta dot, phi dot. That is q dot to this term. Half, right? So then, okay, t here. Let me see first that r dot, theta dot, phi dot. That is this one, right? So now you are going to find t. Then you are going to compare with this result. So t should be diagonal, right? Because you have r squared, r dot squared, theta dot squared, phi dot squared. So there's no off diagonal term. Then at least you can have, yes. Then diagonal term. So diagonal term, if you do this, make sure you know the first one is only r dot square, so that is only m, right? And the second one is mr square. Third one is m r square sine square. sine square theta. So from here to here, you need your knowledge. If you're familiar with this matrix products, then you can rewrite and in terms of this. So they are equivalent, right? Now we got t. This is the way, if you have more experience for this, so you can easily find t. Okay, so now let's see. T is m0, 0, 0, m r square 0, 0, 0, m r square sine square t. Once we have t, how to find t inverse? If a diagonal is very easy, right? If not diagonal, it's so difficult. So diagonal just make the elements inverse, right? Okay, so here we have A 0, we have t, so now we can, and L naught is negative, okay, here. L naught is negative V naught, right? So all we have. And now we can construct Hamiltonian. So Hamiltonian is half of P. Let me first write down this, and then we're going to substitute. So here, half of P. P is okay. Let me first. This is 0, right? Because A is 0. So P minus 0 minus L naught. And now half of P minus L naught, right? Then that's half of P, which is P is we have a P R, P theta, P phi, right? You just write down since we use the coordinates is R theta phi. Then you just you give it name. So now the T inverse here, right? M 0, 0, sorry, M1 of M, 0, 1 of M R square 0, 0, 0, 1 of M R square sine square theta. Then the colon PR, P theta, P phi. Minus L. L minus L is minus V, so that is plus V naught. Or V. I think V naught is V, right? So here. No. It's here. So I just immediately cut this. Now we can just, you can do the product. You can do this product first, do this, and do this. You can see also diagonal, so this is very easily half of, if you take M outside, or take M outside is fine. Okay. So I take M outside, so you can see the first term P R squared, right? Then you have second term P theta squared over R squared. Third term P phi squared over R squared sine squared theta plus V. And we know this is nothing but kinetic in this spherical coordinates, right? So this one compared with okay, this is the first example. Let's do another example, which we have a linear term. So example 2. L, let's just get directed to your L. This is like particle move in this electron field. So we have electric potential, we have magnetic potential. So that is T minus V, which T is simple, M x r squared. I think here do I need that? Fine, that's fine. Okay. Y dot squared, we just in the condition. Kinetic minus potential energy first is a charge, okay, right? Charge. So that is electric potential, and plus charge, this is a vector field A dot product of V. Okay, which is Q I x from 1 to 3, right? A I x I dot, right? Same thing. So because it's V x V y V z, we just say as x dot. So now you can see here, I have L naught. We're going to rewrite as L naught and Q dot A plus half of Q dot transport T and Q dot, right? They're going to compare with this. So L naught is which one? It's only this term. Zeroth order, right? So that is negative Q. Then what is A? A is this term, right? This first or linear order of this general velocity is that's QA, right? QA. Or that is a QAX, QAY, QAZ. So here A is not equal to 0. Then now we are going to find, so that is with this L1, right? So we need to find this. Now we are going to find this, right? T. So here, T is, because this T is half of M x dot square plus y dot square plus v dot square. And if we want to write half of x dot y dot v dot, this is a T is x dot y dot v dot. Then your T from here, this is our T. So from here we can analyze the T is which form. Again, since we only have this project term, so the matrix T should be very simple, only diagonal term. T should be M 0, 0, 0, M 0, 0, 0, M, right? Very simple. Since this product is equal to this, and only when we have the diagonal term, right? Okay, then the T inverse, also very simple, 1 over M, 0, 0, 0, 1 over M, 0, 0, 0, 1 over M. Okay, we have A, we have T, now we can go back to construct Hamiltonian. So finally, Hamiltonian is half of P transport A transport and T inverse and P minus A and minus L naught. Then let's substitute those. P is Px minus Ax, Py minus Ay, and Pz minus Az, right? As, Ay, Az is here. And T here, T inverse is 1 over M, 0, 0, 0, 1 over M, 0, 0, 0, 1 over M. And here this is Px minus Ax, Py minus Ay, Pz minus Az. Now finally, minus L naught. So L naught is minus Q what? So that's plus. Okay. Then this product, you will see this also diagonal is very easy. So finally, you can see this half of this M here in the denominator, and then the others are this. It's very simple. Summation I from 1 to 3, Pi minus Ai squared. And Ai is, okay, let me just substitute. Ai already here is Q Ai squared and plus Q. So if you has more experience to try very easily, you know how to determine the T. I think this construct used the matrix unit is easy, right? You don't need to make a x dot and find x dot in terms of px, py, and others. So you need what you need to find from the summary here. Find L naught. Of course, you need first write down time to the Lagrangian. Then you can determine which is A, which is L naught, which is T. Then you just substitute here. Okay. it depends. Some case maybe this one is easier, but some case other. So that is now we just do some first introduce a matrix representation of this canonical equation of Hamilton matrix equation of motion in terms of matrix in this chapter. In chapter 9, we are going to use that matrix representation to discuss general way how to solve the equation. So in order to apply this, we are going to first introduce. This is a very elegant and powerful tool. Matrix representation for canonical equation of Hamilton. That means we're going to write down in terms of this matrix representation of this equation motion. So define. How to define matrix? So we are defining eta as a column matrix, which is formed by general coordinates q1 until qn and p1 to p1. So this coordinate is 2m plus multiply 1, right? So because in the phase space we know this dimension is 2m. With the first side, right? So that is so eta I equal to qi with I and j from 1 to n. Then this equal to pi with j from n plus 1 to n. That means we just combine these two we call variable. Actually, they are also called canonical variables since the relation between these two has a canonical relation, right? So that is we define. If we define this, then look this eta dot. It means total time derivative, right? Let's do the derivative, and then we are going to do the derivative to each individual, right? Inside q1 dot qn dot and p1 dot pn dot, right? Each individual. Then from this canonical equation of Hamiltonian, we know the q dot is equal to partial h partial p1, right? q1 dot and then partial h partial pn, right? That is for qj dot. Then pj dot is negative partial h partial qj, which is q1 for the p1 dot, and for the pn dot, which is partial h partial qn. So, and now you can see here what happened. If in terms of the partial Hamiltonian partial, this general coordinates, they just reverse, right? This part go to the first part, and this part go to second, and we have a negative sign. So if we write down in terms of a matrix, I'm going to introduce another square matrix J, and multiply partial h, partial q1, partial h, partial qn, partial h, partial p1, partial h, partial pn. That means as we order, still in this way, is that qj in the first half and pj in the second half. So then you see this difference. So we introduce j, which make this difference. Just the j, the goal of j is just try to reorder this element. So you can immediately know the j here must be, I'm going to use this way. 0 in this diagram, n multiply n matrix is 0, and 1 is n multiply n matrix, and this minus 1, which is unity matrix, and this diagonal is still this 0, n plus n. So actually it's 2n plus multiplied by 2n square matrix. So here this means it's n by n, 0, 0, right? 0 and 0, all are 0. N by n. This means this. And 1, n minus by n is 1, 0, 0, 0, 1, 0. So only these diagonal terms are 0, other are 1, other are 0. That is this. Then you can see, if I use the J, it is indeed can reorder. So you can see here, this one, the first half of this one multiplied, right? This multiply the first half, 0, so there's no dot. And then the second half is this one, right? This one multiply this half, second half. So that is this one. That makes sense? Okay, I will not write down the sentence, I just explain why this works. And then this negative is this one, right? This one multiplied here, the first half, that's negative. And this one multiplied second half, 0. So that means now we can rewrite, use this way. Eta dot is G, that is matrix is, just say partial edge, partial eta. So this one, let me try to give the definition. Partial edge means partial, eta is partial Q1, partial edge, partial Qn, partial edge, partial P1, partial edge, partial Pn. So, make this very simple formula is equivalent to this canonical equation of motion, but we make matrix representation. So that is canonical equation of Hamilton in terms of Hamilton, in terms of matrix representation. Okay, just time, so let's stop here. And I think next Tuesday we probably will finish the chapter 8. So we will discuss some general, like cyclic coordinates, conservation, symmetry. Then we took some of example to play and compare with Lagrangian equation and or Lagrange formulation of mechanism and Hamiltonian formulation mechanism. Compare with both. You can solve the problem either use Lagrangian or Hamiltonian, and compare both. And later, the Hamiltonian is more powerful, is developed to other fields like quantum mechanics. So that's why this Hamiltonian formulation mechanism is more powerful with Lagrangian. Okay. Good. Yes. Okay. Thank you.
Never had it. Why you are on backbencher? Hello. One more.